聞けばできるかもしれないです。
All right. I hope moving forward.
I added the
Yeah,
UI.
thank you.
The problem is that the dataset command is specific to JWST, and so I have a JWST format, because you're submitting to a different journal. It'll have a different font and link type. So do you know if you've done the UI before you submit this?
I have no idea, but I can check.
Yeah, I copied and pasted it from my paper. It's just the command.
Okay, then I will do that.
Okay, thanks.
Do you know what to do?
I have no idea. Maria Teresa is already tested? Or?
Everything's tested.
Okay, good.
It looks like, oh, good. Maria must be sharing her screen.
I think so.
Good. Maria, can you unmute and just say hi in case so we can hear you? Maria Teresa, if you can hear us, unmute and say hello. She's going to go remote.
Maria Teresa, can you hear us? I guess so.
Oh, she's unmuted. All right, can you say something, Maria? Maria Teresa?
Hello? Could you hear me?
We don't hear.
We don't hear you.
But
Oh, okay.
yeah, she looks unmuted.
I am unmuted.
And can you turn on your video too?
Could you hear me?
Let me see if she's trying to chat.
Could you hear me? I can hear you. Could you
So
hear me?
please take your seat. We are starting soon. Next speaker is online. Let us check the audio and so on. Please wait a bit.
Somebody turn
Could you hear me?
room volume? Yeah, can we turn up the room volume, Kevin? Can you turn up the room volume?
Could you hear me?
Okay. Now
Getting better. Getting better.
Great.
Could you hear
Can you
me?
turn on your video by any chance?
Tagashi, could you hear me?
Yeah, but still.
Can you turn it up a little
Yeah, we are starting to hear you. Wait a bit more.
Because I am at the maximum volume for my laptop.
Okay, yeah, it's still, we hear something, but it's still.
Yeah.
So Maria Teresa's side is, she said this is maximum. And then.
Kevin, is there,
Now,
are we
could you
able
hear me?
We are hearing you, but still.
Wait, Kevin said, wait 1 second.
Yeah, please wait a bit.
Maria, can you please just keep talking?
Okay.
But
Okay.
don't start the presentation yet.
Did you see my presentation?
Please wait, but could you
Okay,
keep
okay.
talking something?
First, hello everyone.
Hello.
First of all, I would like to apologize for not being able to attend in person the meeting, and I would like to thank the organizer for the opportunity to talk about the transient search on Euclid images on behalf of the supernova
Maria
transient
Teresa,
working
please
group.
wait. Maria Teresa,
Yes.
please don't start your presentation yet. We are testing the audio here.
Okay, okay. But you can hear me?
He's saying, okay, we're at max audio.
Okay.
Maria, can you get closer to the microphone?
Yes, I am. I have the microphone near. Can you hear me?
Your yes was really good, and then you faded away.
Yeah,
Can you hear me?
we hear you, but the sound is quite small, and it seems it's not the issue of our side, if I understood correctly.
Oh.
Could you?
That'd be even worse.
Yeah. Maria, are you able to move closer to your microphone or not?
Now we don't hear you at all.
But everyone online says that they hear her very, very well. So that
okay.
might be.
Then yeah, that's our issue.
Okay, so maybe we're at max audio, Kevin. All right. Well.
Okay.
Yeah. Maybe that's.
Yeah, let's all just be very quiet and make our ears like, the TNT. There you go. See? Free advertising.
Yeah. Okay, then let's do it. So.
I cannot hear you, Tagashi.
We will be very quiet and listen to you carefully.
Okay. Could I start, Tagashi?
Please start.
Okay. Everyone, first of all, I would like to apologize for not being able to be in person for the meeting. And also, I would like to thank the organizer for giving the opportunity to present a transient search for on behalf of the Supernova Transient Working Group, and for allowing me to do so remotely. Euclid is a mission built and operated by the European Space Agency and with contribution from NASA. The Euclid consortium, consisting of more than 2,000 scientists from 300 institutes and in 15 European countries, the USA, Canada, and Japan, provided the scientific instruments and the scientific data analysis. The Euclid Pay module is designed around a 3-meter telescope with a 1.2 meter primary mirror. The Crook plate divided the lights into optical and near-infrared components and direct them to the two onboard instruments, a visual imager, VIS, and an infrared spectrometer, photometer, NISP. This has a field of view of 0.57 square degrees and with a pixel scale of 0.1 arc second per pixel and a resolution of 0.2 arc second. This instrument is equipped with only one broad band covering the wavelength range from 500 to 900 nanometer. The NISP instrument shares the field of view with NISP and is the largest field field of view for even flow in the space for a near-infrared instrument to date, and has a resolution of 0.29 and a pixel scale of 0.23 arcsecond per pixel. NISP provide both multi-band photometry with 3 broad bands, Y, J, and H, and slitless Grism spectroscopy with 2 channels, the red-green passband and the blue-green passband. Here in this figure, there is the spectral response of both optical and near-infrared bands plus the 2 spectroscopic channels. The largest fraction of the observing time is devoted to a wide survey covering more than 1/3 of the sky area, delimited by the blue contours in this figure. And this survey, wide survey, is complemented by a deep survey taking about the 50% of the total observing time, covering 53 square degrees, to obtain, again, on depth of about 2 magnitude. A small fraction of this, the observing time is devoted to observe 6 auxiliary fields to calibrate photometric redshifts, and another field for photometric self-calibration called the self-cal. The deep survey consists of 3 fields: the Euclid deep field Nord, covering 20 square degrees, was chosen to maximize the overlap with a deep field surveyed by Spitzer Space Telescope, the Euclid deep field Fornax, covering 10 square degrees, that encompasses Chandra deep field south, and the Euclid deep field south, that is the largest of the 3 fields, covers 23 square degrees, and are not been observed by any deep survey to date, but is planned to be observed by Vera-C Rubin Observatory and Roman Telescope. Here the timeline of the mission and the tentative release schedule relative to the start of the nominal mission. Euclid was launched on 1st July 2023, and commissioning and performance verification phase lasted 3 months. The nominal mission started on February 24 and is planned to last 6 years. The overall mission is expected to be at least 6.5 years. The well-characterized and validated data from the processed by the science ground segment will be made public with 3 main data releases. All these data releases will contain all the data set of Euclid for the first year of the survey, year 1, the first 3 years of the survey, year 2, and all the complete survey, year 3. Before each main data releases, there are public quick data releases, and to provide a preview of the upcoming data. And the first quick release will occur next week. Here, the first 5 images acquired by Euclid, released on November 2023 to illustrate the Euclid potential. The primary goal of the mission is to investigate the nature of the dark energy and dark matter by measuring the accelerated expansion of the universe and the distribution of the galaxy. And so the strategy of the survey is designed to create a 3D map of the universe by observing a wide area with a great depth. But the Euclid wide field, high sensitive, and high resolution make it ideal for transient detection. In particular, the opportunity to capture simultaneously optical and near-infrared images is a unique opportunity for transient science. And the repeated visits of the Euclid fields can be used for a transient search, enabling the difference image analysis. We also have another important opportunity from Euclid survey, and is that we can exploit photometric spectroscopic redshift for the galaxy surveyed for transients, and these are provided by the Euclid consortium. There are several science cases that can benefit from the Euclid data. For example, the high sensitivity of near-infrared images can be exploited for type 1a supernova cosmology studies, or and also to discover intrinsically red and faint transient in the nearby universe. The high resolution of optical images enable us to discover transients near galaxy nuclei as the tidal disruption events, and the incredible depth of the optical images enable us to discover high redshift transients, lensed supernovae. Finally, the wide field of view of Euclid allow us to collect a larger sample of supernovae in a large range of redshift to measure their rates as a function of the cosmic time and the galaxy mass, the star formation rate, etc., etc. To leverage this opportunity that the Euclid data can provide, our working group developed several projects aligned with the main data releases of the mission. First of all, we analyzed the data from the quick release 1 in a study led by Chris Duffy that will be published shortly. We cross-matched all the transients reported by the transient name server with the Q1 data and to find the transient that especially overlap with this data. And we found 161 objects that Euclid observed, and by chance during the observation released with Q1 data. And approximately 70% of the non-transients reported in 6 months to the transient name server in the 6 months before the Euclid observation, and with a discovery magnitude brighter than 24, were detected on the Euclid images. And our observation include one of the an early near-infrared detection of type 1a supernova about 15 days before the peak. For example, a very late detection of an enigmatic or collapsed supernova more than 400 days post-peak. We also can detect on the Euclid images the host galaxy of some transient classified as orphan, and some example on the images on the right. You can see in the left column the legacy survey images, in the middle the Euclid images centered on the position of the object, and the right side the host galaxy we detected. But it was the repeated images of self-cal field that we want to demonstrate the capabilities of Euclid to detect transient both in the optical and near-infrared images, performing difference image analysis. Self-cal field is a 3-square degree field that Euclid has been monitoring every month since the performance verification phase. And to this end, we have requested and we have proposed a K project to the Euclid consortium, and we have requested obtained a very early access to the raw data, and we have developed a pipeline to reduce them immediately and start with a follow-up campaign for the brightest transients and the most interesting objects. The goal of this key project is to measure for both type 1a core collapse supernova, their rates at a redshift, where measurements are rare and sparse, and also to collect some very late and very early near infrared photometry for type 1a supernova, and discovery and study superluminous supernova at a redshift where their discovery are still rare. The pipeline we developed for the difference image analysis is based on Python and other public software as SWARP, Extractor, and LACOS. And we can divide this pipeline in 3 main steps. The first step involves the processing of the single epoch image and to obtain the stacked images of the dittered exposure, followed by a reference image subtraction and detection of the transient on the difference images. The second step involves the comparative analysis of the multi-epochs observation, and to select the transient that have multiple detection and to collect the light curves. The final step obtain the photometric classification of the selected transients, exploiting external data as the photometric redshift provided by the Euclid consortium or data from the spectroscopic follow-up of the brightest transients. This is an example of raw images in high band, raw images in the near infrared band. The most critical step for the processing of the raw data is the removal of cosmic ray from the optical and the correction for the persistent charge effect for the near infrared data. You can see here a NISP observation sequence with a long exposure time spectroscopic observation followed by 3 shorter time photometric observation with the residual signal of the first image on the subsequent images. Here an example of the stacked images that a small part of stacked images that we obtain by combining 4 dittered exposure with a zoom in section to show the incredible details that we can see, and finally here some example of the difference, the detection of transients on different images. You can see on the right the reference image, in the middle the search image, and on the right the difference image. And we are detecting we are selecting all the transient sources that have a minimum of 2 detections, and perform the forced photometry for in all visits of the field, and to collect upper limits and measurements, obtain the light curves. Here the example of 2 different selected transients and their corresponding light curve. Then we performed the forced photometry on near infrared images, and to obtain the multi-band light curves. Here there is a nice example of a transient discovered both in Y and H bands images, and this is a bright transient supernova, and we can follow its photometric evolution for more than 400 days in the optical and 200 days in the near infrared images. The last part of the pipeline is devoted to obtain a photometric classification for all the selected transient by fitting the multi-band light curves with templates, and more details in the poster by Luca Izzo, who is overseeing this part of the work. In some cases, the photometric classification is validated with spectroscopic classification obtained with different programs at LBT, Subaru, Gran Canaria Telescope, VLT, etc., etc. We are also working on gathering information on the redshift for the host galaxy to use it as prior for the photometric classification, and we can both exploit the photometric redshift measurements, but also from the Euclid catalogs, but also the NISP observation. Here an example of transient discovered in the host galaxy, and bright host galaxy, and on the right you can see the trace 1D spectrum, NISP spectrum, with the trace of the galaxy and a faint signal in the supernova position. To date, we analyzed the 17 epochs, detected 1,300 supernova candidates, and the preliminary results from the transient photometric classification confirm that we can detect supernovae up to redshift about 2. These preliminary results are in a perfect agreement with a simulation that have been performed before the project began, both in terms of the number of transits that we can detect per each single visit, but also for the magnitude and redshift distributions. But the best is yet to come. Our upcoming project related to the data release 2 and data release 3 will focus on the integration of the Euclid and LSST data. The combined data set will cover a larger range in wavelength, and this is an important opportunity for transient studies. With this larger coverage, we can improve both the photometric classification of transient, but also the accuracy of the estimation of the photometric redshift of the host galaxies. And there are several science cases that can leverage this opportunity. And there is a huge effort on the way between the two communities to define the data that can be shared, and some initial recommendation have been published 2 years ago with the contributions of our group, and we propose to share the joined light curves, but also image cutouts, information on the position of the object, on the host galaxy redshift, and in general on the detection efficiency of the survey. In the last workshop organized by the implementation group for the derived data products, our working group proposed 2 projects. The first one led by Isabel Hook and Chris Duffy, that aims to exploit, to analyze transients that exploded in the area covered from both the Euclid-wide survey and the LSST-wide fast and deep survey, to maximize the number of the transients that have both optical and near-infrared measurements, and also to study, for example, the host galaxy of orphan transient detected by LSST. The second project, led by Vincenzo Petrecca, Luca Izzo, and myself, aims to exploit the simultaneous rolling search from both Euclid and LSST on 2 deep drilling fields, the Euclid Deep Field South and the Euclid Deep Field Fornax. And the aims of this project is to collect a complete sample of transient with very well sampled optical and near-infrared light curves, and also to compare the optical and near-infrared searches. Here an example of the the overlap of the observation on the Euclid D field south with a zoom in on the first expected overlap in January 2026. We aim to work to analyze both the images and the catalogs, combined images and combined catalogs, to cross-match the detection, but also to obtain the joint optical and near-infrared light curves. And Vincenzo Peterecca will give more details on his talk. And finally, my 2 cents for the discussion. I think that a unique opportunity for transient studies for the coming year is the simultaneous search from space and ground-based telescopes. And Euclid and LSST synergy can serve as a primary example for what we can realize in the future. And for example, for Roman and L Rubin synergy. Thank you for attention.
Any questions here? Steve, maybe you need to use microphone.
Okay, good. Okay. It seems that Euclid is not covering the LMC, and with Roman, it felt like they're also not covering the LMC and SMC. Is there a particular reason why the LMC was skipped for Euclid, and whether Roman is observing the LMC or SMC?
No, I think it's covered by the wide survey, so with only one, only one single visit.
Oh, okay, good. Thank you.
Hi, hello? Yes. Hi, this is Yair Kavi. Thank you. This is really beautiful. I might have missed all of this image subtraction and transient finding is happening after in the quick data release, or is it happening in real time, and can there be alerts in real time?
No, in real time. In real time, we have a special area set to the raw data for some for the Euclid fields and for self-cal. The analysis of the Q1 data is on a single visit, a single visit data release. And this will be the case of the Euclid-wide survey. So in the Euclid-wide survey, we can manage one single visit, but for the Euclid deep fields and the self-cal fields, we have repeated visits, so we can perform the difference image analysis.
Yeah, just to add, we are doing the on-live, as Maria Teresa said, and then what we reported, we haven't reported TNS live. We are discussing what to report. Euclid has a crazy restriction on data release and so on, so we are trying to figure it out. Okay. Question online?
Do you know how much time
we don't have much time, but
I'll pick one. I'll pick one. How about, is there an attempt to identify stellar transients in the data?
No. Stella?
Then we can take the next one as well.
Okay.
No.
Is there an attempt to? Is there an attempt? Go ahead.
No, sorry. We now are classifying all the transient sources we found in the first 17 epochs. So at the moment, we found that the majority of these objects are supernovae. So I don't have idea about transient stellar transients.
And is there any attempt to coordinate Euclid and Roman to have faster semi-regular cadence?
Yes, this should be my question for the Roman community. I think if Roman is observing the Euclid field south, to coordinate the observation, to have simultaneous observation with the Euclid and in the optical, Roman in the near infrared would be great.
Good. Then let's move on. Thank you very much, Maria Teresa.
Sharing.
Could you stop sharing your screen,
Yes.
Maria Teresa?
Yes, okay.
Yeah, you can see here. And your time is- Have you stopped, Maria Teresa? We still see your screen. Ah, yeah, good. Ah, good. Changed. Thank you.
Sorry.
Then let's move on. We next have the talk by Nao Suzuki. So please go ahead.
Okay, thank you very much. So thanks for having me here. This is us. I was surprised to see the air condition got turned on February 2nd. Okay, so this is since some of first time to see, so this is my one-page summary of my academic career. I started from the Big Bang nucleosynthesis and have been working on the precision cosmology. And I know a lot about the quasars and work on the type 1 supernova cosmology. And I'm leading with Takashi, leading hyperspin type 1 supernova cosmology using the both hyperspin on Super in the Hubble Space Telescope. And we are finding something exciting, and the French team is developing a new light curve feeder called NACL after salt. Okay, so we are aiming to unblind this summer, and we will aim to report soon. But please don't ask me the definition soon. Okay. So today I have two proposals to this entire transient community. One is the imaging transient screening by comparing two space telescopes. So this is the thing at the end of the question we are talking about. And the space telescopy transient screening for every single spectrum, and why we want to do this. So this is the thing at this workshop, as long as I. Okay, part 1 imaging and part 2 the spectroscopy. As we have discussed, all of the talks so far and in the afternoon is talking about this yellowish part. Okay, so this is the repeated observation. The rest of the sky is so big, and we are left untouched. And Euclid is going to do the 14,000 square degree entire, almost, except Milky Way survey. And the Roman Space Telescope, I to be exact, 2,400 square degrees. And this is taken from the core community report. So this is the wide area, and this is the medium area. And here is the surprising thing. So this is the not the trans. This is the wide area for mostly for weak lensing and BAO, but they got the deep field. How many folks did you know they got the deep field? One. Can I take a picture? I need to send this. See, you have to read this, okay? You have to read the report, but nobody reads the report besides transient part, okay? They got the 2D field, and the cadence is not discussed. So as a community, one voice, we need to raise the voice. We wish to introduce the wide field. This one was that Cosmos and the XML field are not chosen by a Roman transient team because it's not the continuous viewing zone, but we can do a great science. Okay, that's one. And can we find supernova without subtraction? Okay, so this is the question I'm trying to answer. So I suppose everybody in this room knew these two great supernova hunters. One is Fritz Zwicky. He is taking the data and of the photographic plate using the microscope, he is finding supernova all by himself, by eye, without subtraction, without digital image. I done this from books.
I've done it myself.
Excellent. He came to the office early in the morning, and then he couldn't read the this. So, and Itagaki-san, of course, I suppose everybody in this room knows Itagaki-san. Do you know how he finds the supernova? He doesn't use machine learning. He doesn't use subtraction. He takes the new data and they compare one by one and finds the supernova. It's what human brain can do. And this is the AI age. So that's what I am trying to do next decade. Okay. So this is a JWST comparison. So I'm part of a Cosmos Transient team, so as the hobby. So this is the nice discovery, so you can see the dots. And then for this discovery, I use the subtraction and find these tiny dots. So this is easy part. But can we find supernova without subtraction, without repeated observation? Okay, so here is the JWST against Hubble Space Telescope. I tell you, there is one supernova. Can anybody find it? I will give you 10 seconds. There is one. 2, 1.
Too many
0. That's right. It's the data is rich. It's here. Okay? And it's obvious, right? If you find it fast. And the redshift is correct, and it matches to this photo scene. So this is the genuine transient. And you can, this is, by the way, this is not a repeated field. So I can find this by either. And the same thing is happening. So first time I saw the JWST data, I was so excited. There are so many red dots. Everybody got excited, and everybody thought it's a transient. But it turned out to be, it's not the transient. These are the what we call little red dots. And everybody, every week we see some papers about this. It turns to be an obscure agent. It's a point source. And compared to the HSD images, you can get to see this is really high redshift AGMs. And the byproduct, I'm finding something interesting. So this is a gravitational lens. So that Einstein calls something is missing, but you can get to see these gravitational lens by comparing to the other facilities. And the asteroids and the mysterious object is also happening. So I can get to see these asteroids. So this is a one-time event. And then sometimes I see the trail of asteroids. And this is a very mysterious object because this is a nearby asteroid. And I expected to see most of the asteroids should move, but this one doesn't move. It could be just one flash thing. Sorry, it's okay. Mic was off, sorry. And these are the genuine discoveries. So JWST, if I compare JWST, Hubble Space Telescope, and we can get to know the SED and the SED fit, which matches to the expected redshift. However, if we don't see the host galaxy, it's very hard to see if this is a transient or not. But the little red dots are very interesting objects, so it's good to find them. So I'm referring to the host galaxy hosted supernova. So we should be able to find these guys. And the second part I want to discuss is the spectroscopy. So this is also untouched field. Okay, what do I mean by that? So Euclid is going to do a Grism survey, and it covers 14,000 square degrees. So number of spectra is 1,700 spec Z per square degree. And the Roma is also doing that, and this is taken from community core survey, which is still, I think, changing, so this number may change. So the resolution-wise, it's about the same. It's about 450, and it covers 2,400 square degrees. So this yellow region is the one we expect to see spectra. So Euclid is going to reproduce 23.8 billion spectra. And the Roma is going to produce 19.1 million spectra, which is a lot of spectra. But you have to read the lines between the text. The reason is this is the secured spec Z with emission lines. So as this Roman number, okay? So number behind this is order of billion, okay? Billion spectra are taken because they're slitless spectra. All of the targets are inside the spectra. So if you can do a good spectral extraction, potentially you can get to see billion spectra. Okay, so that's the future which is happening in 10 years. And then nobody, as far as I know, discusses in terms of transients. Okay, so can we discover supernova in galaxy spectra? Okay, so that's the question. So this is what I have been developing. So this is the stack of all of the wine spectra. And I thank you to the WISE-REP people here. I took all of the data from the WISE-REP, and I developed the PCA time series, which is here. So I claim using a 3 again spectra, I can reproduce entire light curve. Okay, so only 3 instead of many 1 by 1 feet. I can reproduce entire light curve, so as the 1BC quark collapse and type 2P. And I aim to implement this to the next generation light curve filter called NACL with the French team. So these are all eigenspectra. And I wish I need to get the more spectra. So I want you to give me a bulk download thing, okay? So if you are interested in how to do it, it's written in my Quasar PCA paper. And then same thing can happen to the galaxy. So this is the eigenspectra of galaxy and the eigencoefficient of galaxies. So this is the coefficient distribution eigen spectra 1 and 2. There is a boundary because it's got the, so this, if you go beyond the boundary, there's a negative emission line. And the nature doesn't allow to do this, so I have to know the distribution as well. So if I have eigenspectra and this distribution, I can describe millions of gazillions of number of spectra using only 4 eigenspectra. That's what we have been doing for the STSS. That's what we have been doing for the DAISY. Okay, so Quasar eigenspectra is still mine being used. Okay, so here is the proof of concept using the STSS STScI survey galaxy spectra. The top panel is observed galaxy spectra in black, and the red one, this one is the galaxy-best galaxy spectra. So if I subtract that, I can get to see type 1 supernova. Okay, so this is just a PCA fit, and I can get to see type 1 supernova from just galaxy without imaging. And we tested this, and we can find many type 1 supernova. This time we tested only type 1F, but we can get to see this. And the rate is about 1 in 6,000. Okay. Then can we try and do the same thing for JWST? So if I go to the, this is Gabe Brahmat's web page, Dawn, everybody knows Dawn DGA page. So Dawn JWST archive, which is great page. And I can download all of the public domain spectra. So this is the collection of entire JWST data, which in the last 2 years, first 2 years, okay? So you can get to see every single line corresponds to the one spectra. So this is how much we have. Okay, so I just took the signal to noise ratio greater than 5. And since I'm at the Space Telescope, I got the request. Gabe's download and the scripting and the scraping is very easy. Please improve it. It's too hard for me, okay? So I want you to do bulk download, but it's not that easy at this moment. If I use the Gabe's thing, it's super easy. Okay. So this is the compilation. So I did some compilation. So this is redshift 1, 2, 3, 4, 5, 6, and 12. And I tell you, most of the paper, I think 95% of paper comes from this region, okay? So this is a press release by Nakajima-san, and he's studying galaxies beyond redshift 10. So most of the paper comes from only the top part. The rest, I think not many people are studying these parts, so I will take advantage of it, but the data is beautiful. I will show you everything, okay? So what I do is I put it in the rest frame. So this is the rest frame, and you see trace. So this is the galactic thing, by the way. And I combine with the time series from the supernova, okay? So before I show you, let's do the homework. So can we find the spectrum from JWST's data? So back on the envelope calculation. So this is the Hubble diagram of the host galaxies. And this is the characteristic luminosity. So if you go higher redshift, galaxy gets fainter because they are not matured enough. While type 1 supernova, for instance, we expect the brightness doesn't change much. So this is the comparison supernova versus galaxy brightness. So if you take a look at the galaxy and supernova picture, it's almost the same brightness. And to be exact, 15% of the supernova is brighter than galaxies. So if I take the spectra, some fraction supernova exceeds the galaxy light. So that's the goal. And the STSS, once again, has 1 in the 6,000 galaxy. We can find the type 1 supernova. So I expect to see something happen. So as of today, we have the 7,000 archived spectra. So the expected number is 1. Can you find it? Okay, I will show you everything. So this is the my fit. So first of all, the spectra is not well flux calibrated, and I have a request to the Space Telescope team. Use my black body spectra and do it. That's it, right? Good answer. And the reason why galaxy spectra goes this way is because the JWST published in Jansky. So since F new, that's why it's tilted this way. And as you can see, the majority is between 0 to 5. Okay, we haven't reached beyond, and all of a sudden, well, it stops. So this is all. For this purpose, I excluded a low signal to noise ratio. Unfortunately, I didn't win this time, but it doesn't mean I cannot find it. So next time, if more spectra happens and we fine-tune our technology, we should be able to find it. And billions of spectra exist, then we should be able to find a good number of spectra from Roman and from the Euclid, okay? And follow-up priorities. So I want you to make these spectral detection as a default so that everybody should be able to find these supernova automatically. So this diagram, so how do we compete among each other? So last 2 days, and including today, everybody discussing interesting targets. Supernova type 1, of course, quark collapse, gamma ray burst, and of course, neutron merger, and many, many interesting things. So if we keep, pushing the priorities to the DD time, we need to have an objective ranking system. So this is my proposal to you all. Does anybody know Zipf's law? Okay, so this is the ranking on x-axis, and this is the frequency of the word. Okay, so this is many, many languages: Latin, German, English, Ukrainian, Spanish, etc., etc. The striking thing is it doesn't matter which language, but this ranking, the slope is the same. Isn't this amazing? So how often does it happen? So if you rank them by the how often does it happen? So for instance, we have detected the neutron star merger, and we want to find a redshift 10 pair instability supernova. And then maybe we can find a black hole merger afterglow, which we haven't seen that yet. And of course, supernova less than 1 megaparsec is high priority. And at the end, we wish to see galactic supernova. So presumably, this is the most precious one and less frequent one. And if we can agree with this, and every community can give our director to this ranking, director can rank them without knowing the detail. Okay, so that's my proposal. Okay, so this is my summary. So my proposal to you is next time, starting cycle 5, I wish to have a checkbox. Is it okay to do that transient screening on your behalf? And most of the galaxy people do not care about transient, but every galaxy proposal, we should try to find transient. And my conclusion is, can we find supernova from single epoch? And yes, we can, because Euclid and the Roman, if I compare side by side, it's easy. And I didn't get a chance to get permission, but you can see my computer over shoulder. I'm finding a Euclid supernova. So, and can we find the supernova for galaxy spectra? This time I didn't succeed, but yes, we should be able to do it. And you can do JWST Euclid. By the way, the resolution of Grism spectra, Euclid and Roma is similar to what I showed you. So that's enough resolution to identify supernova. And I wish to end my talk with the quote from the first director of Space Telescope Institute, Robert William. I got a chance to interview him, and he said, "Sky is for everybody." Thank you.
Thank you very much. Any questions? Yeah.
This is great, but I had to understand this better about this subtraction of the spectra in order to find supernovae. The subtracted galaxy spectra, are they some kind of a composite of eigenvalues, or?
Yeah, that's right. It's the sum of the eigenvalues. I mean, eigencoefficient. Eigenvalue is something else.
Yeah.
Yeah, kind of follow up on that question. I like that example you showed earlier. You can see the JWST images. Is there a time difference between those images, or this concurrent imaging? Like, how can this apply for transients that might have longer time scales?
So we can study the time difference. I showed you HSC taken many years ago, so we are sure it's not there.
I can take one more question. If any, are there anything online? No. We can take two.
So there's great stuff there now. But my question is, there's a supernova right there. What science do we do with it? What science do we do with that supernova right there?
What science?
Yeah.
So I think soon enough, everybody, including Rapid, we can classify that just from the one SED. So if it is interesting, we study that. If it's not, we can count as one of the rate studies.
So you think there's enough information in that one snapshot?
So for instance, we are detecting the hypersymmetric supernova, and we sent the best ones to the HST. We budgeted 20% errors, but I and David Rubin worked very hard. We didn't make any mistake. So that's the status these days. So we should be able to identify something with small number of information.
Azri, go ahead.
This is really great, and I love the idea of using single epochs. Have you explored how much contamination you get just from having different filters? Like, I can imagine something that isn't transient, but it's just obscured, which isn't in your HST image, but is in your JWST.
So as far as I know, we have the host galaxy. We are in a good hand. If we don't have, as of today, we cannot tell which is which. I mean, little red dots versus real transient. So that part needs to be studied more. However, by the way, if we can raise your voice and introduce the cadence for the Roman wide field survey, stars are moving. If I compare the HST image against recent JWST, without exception, all of the stars are moving. So we can exclude stars, and we can study the distances. So that's another advantage.
Okay, let's move on. Thank you very much. Next is, let me see how it works. Good. So next is from Vincenzo Petrecca.
Okay, as long as you stay.
Yeah. Please go ahead.
Is this working?
It wasn't working. It wasn't working.
Okay, it's not working. Fine. Okay, hello everyone. So first, thank you to the organizers for being here. I will talk about Euclid synergies with ground-based survey for time domain astronomy. And this is a work that I'm doing with Maria Teresa Botticella, Luca Izzo, Enrico Cappellaro, and the Supernova and Transient Working Group of Euclid. So let's start with this Euclid survey map that you already saw at the previous talk. And there is the wide survey, which is not maybe so important for time domain, but the important fields are the 3 deep drilling fields that will receive about 50 visits for the duration of the survey, covering 53 square degrees. So this is potentially interesting for time domain astronomy. And you can see also that one is at north, and is including the self-calibration field. Then there is this green box, which is showing you the area that will be accessible from Rubin, and 2 of the other deep drilling fields. One is the Euclid Deep Field Fornax, which is including the Chandra Deep Field South, and the other is the Euclid Deep Field South, 23 square degrees, are also LSST deep drilling fields. So this is extremely important. Now, as this is a workshop we are supposed to discuss, I will try to trigger some discussion during this presentation. So first thing, why do we need to develop synergies? Of course, this is coming with a lot of opportunities because Euclid high resolution optical and near infrared data can allow us to detect high redshift and thus abundant transients that usually are missed from ground-based survey. What is the limitation? That the survey itself, its design and its strategy is not designed to do time domain astronomy. And so what we can do, well, you can use ground-based facilities and general synergies with other instruments to get spectra and to get high cadence multi-band light curves, at least for the transient and for the sources that you can follow up. And this can enable photometric classification, so you can understand more about these sources. And another bonus thing, let's call it bonus, is that also the single Euclid passages on the wide survey area are extremely important because from the static science, they can improve the host galaxy characterization and photometric redshift, which are extremely important, for instance, for the supernova rate. And they can also constrain both the early and late detections in supernova light curve. And stay tuned for the Q1 paper by Darf et al. That is going to be submitted. You see some incredible light curves from Maria Teresa talk. Now, what do we need to develop this synergy? Let's talk about the problems. The first thing is a shared and easy to read archive of future observation, because we need to plan for follow-up with other instruments. So for surveys like Euclid that are already planned, we need to cross-match these observing strategies with the other instrument. Thank you. We need to cross-match the observing strategies with the other instrument so that we can try to cope together. And also, this is something that has to be done with surveys that still have to start, like Rubin or Roman maybe. And we also need a lot of tools beyond this planning because we need to cross-match these different catalogs. You need to do host the galaxy association and you need to cross-match the catalog of galaxies as well. And what you would like to do is to have tools that can operate using data coming from different surveys to do, for instance, fitting or light curves for photometric classification. But I heard yesterday and also today someone mentioning about doing different image analysis using data coming from different surveys. And this is extremely important. And we also need infrastructure to store the data that has to be in an homogeneous format so that we can work with this data together. And last but not least, open policies. This is an important issue because if we want to foster collaboration with different communities, we need to do something that at the same time, it is maximizing the scientific outcome from the surveys, but it's also preserving all the equity principles between the different individuals, countries, and communities that are involved in these missions. Now, the first most obvious synergy is between Euclid and Rubin. And you also see this presentation, this slide before. You can do unique transient science. You can study supernova rate up to high redshift. You can do cosmology, nuclear transient, a lot of things. This is a work by Bailey et al. Using simulated data from both Euclid and Rubin. And you can see that there is this extended wavelength range that is extremely important to do your studies. And as Maria Teresa mentioned before, there is an agreement between the two surveys with a series of derived data products that are going to be prepared to enable science, especially focused also on transient with the two surveys. But I will talk about the problems, most of the opportunities. So what are the challenges that we have? First of all, we need algorithm and infrastructure that need to be developed and tested to work with both data together. And another challenge is that the DDF observing strategy for Rubin, which is still has to start, is still have to be defined for the Chandra deep field south and the Euclid deep field south. And so as this thing is still under refinement, there is a urgent need for metrics to be developed so that you can quantify all the requirements that we need for your science cases, so that you can plan the surveys to get the data that you actually need. And another technical limitation is that the Euclid pipeline, the official pipeline, lacks algorithms to do difference image analysis, transient search, and cutout service. We are using a pipeline within the supernova and transient working group that has been developed by Enrico Cappellaro, but we need to scale this analysis that we are doing on self-cal, which is 3 square degrees, on the total 53 square degrees of the Euclid deep field. So the scaling this from 3 to 53 is a bit complex. And this is particularly critical if you want to do a simultaneous transient search and if you want to trigger alerts. If you look at the expected timeline for Rubin, you can see that the nominal start should be about October 2025. Please correct me, someone more inside Rubin if it is wrong. But if you look at this date, you can get two information. The first thing is, okay, you have some time to prepare the things that you need, but you also have a problem because there is more than 1 year of Euclid data that are going to be missed if you don't do something with other surveys. So that's why we need other photometric surveys and other follow-up with other instruments. While we are waiting for Rubin, we are preparing packages to be ready. And this is, for instance, a tool that we developed to take the expected observation from both the Euclid and the Rubin baseline. And you can see here, this is the example for the Euclid field south. All these points with different colors are related to the different filters by Rubin, and the blue stars are the Euclid observations. And you have the nominal start of the IDFS by Euclid is August 2025. Then you will repeat the observation in January and August with this cadence up to the end of the survey. And this is the first overlap. You can zoom in and you can see that there are these 3 or 4 visits by Euclid, all these important visits by LSST. We also have tools that we prepared working on simulated LSST data by the Rubin Data Preview 0. We analyzed the supernova, type 1a supernova rates on the simulations. This is an example of the outcome. And we were trying to understand the impact of all the sources of uncertainty that are affecting the data, which are mostly photometric redshift, host galaxy association, and photometric classification. We found, for instance, that, of course, photometric redshift is the biggest issue because you can use this as a prior for the other things. But Euclid can help a lot with photometric redshift, thanks to the near-infrared bands. And to do this analysis, we also developed tools. For instance, for the host galaxy association, we prepared this that is producing cutouts to rank all the host galaxies. And this has been tested on the Rubin Science platform, and we are moving this on the ESA Data Labs, which is the analog for Euclid, where we are getting the data and we are working on the data. And we are also doing some template fitting for classification. So as I mentioned before, there is a big effort in preparing observational proposals so that we can add other information to the Euclid data. And this is an example of what we've been doing. There are these proposals here with these facilities for spectroscopic follow-up of Euclid discovery so that we can have a classification. And then we have also this proposal that got accepted, which is 1 year photometric monitoring of 4 square degrees in the Euclid deep field south. So it's about 280 hours. And this is extremely important because it will be a pilot project on what Euclid and Rubin are expected to do. Why do we decide to observe this field? Because this is peculiar compared to the other one, because we have additional visits that are being taken during calibrations, and are these visits here. This is a GIF, it starts. No, it's not working. Where it was showing how Euclid is taking the observation, just moving along the field. And we have these 10 visits that we already started to analyze. And after these 10 visits, starting from August 2024, there will be the nominal program starting in 2025. And you will repeat this observation between August and January. So it's twice per year. And a similar pattern is also observed at Euclid Field North, but unfortunately, this is not visible from Chile. And what you can see here is overimposed the Rubin field of view and the VST field of view. So we are covering this 4 square degrees area here at the center of the field. So this is our survey. So it's called VESTA, VST Euclid Synergies for Time Domain Astronomy. And I want just to mention why VST is the ideal survey to do something like this. It has a wide field camera, 1 square degrees. Of course, it's 1/10 of LSST, but still quite big. Excellent image quality. It has the same pixel scale of LSST, 0.2 arc second. Very similar photometric system. It's located in Chile, so the sky should be the same. And we have a lot of experience with transient survey. For instance, the Sudare survey, you can see here simulations done by Enrico Capellaro that are showing the area that you can cover and the number of supernovae as a function of the exposure time, the total time that you can observe for a night. So we have this survey that started in October 2024 with a weekly cadence observing on GR and I bands. So we are currently analyzing the data. Stay tuned for the results. And I just want to show you an example from previous data acquired with the same telescope. It is a supernova discovered by Euclid. You can see the image and the difference here, and also observed later with the VST. And this is just an example of a light curve with an temporal fit, just to show what we can do with this survey as soon as we start. And as another example, but I'm reminding you to Luca Izzo's poster, Luca is over here. This is an example of spectra taken with LBT, which is part of the other proposal for target of opportunities. So this is my summary. Again, Euclid is extremely important, and it can be a powerful transient detection machine, albeit this is not its main scope, but we need synergies with other surveys to exploit these capabilities. We need to enable prompt follow-up, and we need to analyze a very large area. So this is a bottleneck at the moment. And also multi-facility analysis demand a high degree of planning to optimize the strategy, and also data sharing policies and tools and algorithms capable of working with data coming from different instruments. So thank you very much.
Thank you. Any questions? Yeah, Azri?
I think as part of being Rubin observed one of the Euclid deep fields. Do you have access to that data, or do you have to wait for the data release in order to, I think, like start testing some of this out?
No, I need to wait for the data release for that. So I know that Euclid Deep Field South has been observed. Also, Chandra Deep Field South should have been observed. But we will wait for the data preview one. Should be.
It's some.
It's some. Yeah, I have the time. Yeah. Oops. DP1. Yeah, June, July 2025.
Good. Then I think we should move on. Thank you very much. Please do. Yeah. Not this one. Good. Where the micro? Oh, yeah, you can just start. Good. So we have Charlotte Ward. Please go ahead. So yeah, you need to make it. Yeah. So your time is
here.
All right. Yeah. Okay. All right. Hi, everyone. I'm Charlotte. I'm a postdoc at Princeton. I'm planning to talk today a little bit about some more about these efforts to jointly analyze data from Rubin and Euclid, and in particular how we're extending the efforts for the general joint analysis for cosmology to help with the study of transients. And my original talk was going to be focused on gravitationally lensed supernovae, but I decided to expand the scope a little bit. But if you know a lot about JWST, please come talk to me later. Okay, so thankfully everyone has already introduced this very well. We're hoping to combine the strengths of both Rubin and Euclid, where we have the better depths of Rubin and the better resolutions of Euclid and Roman as well, in order to have galaxy catalogs that go as deep and high resolution as possible, so that for blended, crowded fields, we can get the best morphology models and fluxes of those galaxies, mostly for cosmology purposes. However, if you're interested in transient host galaxies and in other analysis for transients, we're working on extending those methods for transients. Okay, so I always like to show this image because it shows how, as we go to greater depths, this is a Rubin-like image here, we reach a point where 30 to 60% of galaxies are overlapping other galaxies. And this is a problem because if you want to know what your potential transient host galaxy is, if you want to get a good photometric redshift, this becomes very challenging at ground-based resolutions. But at a space-based resolution, this allows you to identify what flux belongs to what galaxy, how many galaxies are there, and get good photometric redshifts. So this is obviously important for cosmology folks, but it's also important for host galaxy analysis. We also, for our transient studies, want to combine the wavelengths of the Euclid and Rubin fields. And we also want to improve the cadences by combining data from these different surveys. Okay, from the gravitationally lensed supernova point of view, we will be in this regime where we'll be able to detect, of order 100 gravitationally lensed supernovae each year with Rubin by looking for supernovae that must be magnified because their apparent host galaxy's redshift does not match the redshift of that type 1a. So we know it must be from a background galaxy, and using this method, we can detect of order 100, but many of them will look like blobs in Rubin. So we need to fold in a space-based image in order to confirm that it is a lens, to come up with an initial model of the system, and to extract separate light curves from those lensed sources. And of course, there are multiple methods to do this, but we're advocating for a scene modeling approach, which I'll get into, to help in confirming and characterizing these objects. And this plot on the left here kind of shows the typical angular separation for the population of GLSNE that Rubin will detect, and the median separation is around 0.6 arcseconds. So for most lens systems, they will be blended. So we'll want to fold in space-based imaging in the preliminary confirmation and analysis before doing further follow-up. Okay, so as part of the efforts for the joint Euclid-Rubin derived data products team, we've been developing Scarlet 2, which is multi-resolution forward modeling code where you can combine data from different surveys and model them simultaneously. And the way that you do this is you not only have models for the sources in your field, their positions, their morphologies, their SEDs, but you also have a model for each image, what the point spread function looks like, what the WCS is, what the depth is. So you do a forward model where you render your source models to look like each observation and fit in pixel space in order to model across multi-resolution data. One of the big challenges with this that differentiates Scarlet from previous examples of this approach is that we need to use non-parametric galaxy models. And that's because when you look at space-based resolutions like this, a simple galaxy profile is not going to cut it anymore. We have a lot of structure that we need to deal with in a way that does not enforce a simple galaxy profile. This introduces some challenges, especially in these very crowded fields and when you're coming up with models of low signal-to-noise galaxies. So we do need to use some machine learning techniques to stabilize the scene modeling. So the way that we've implemented this is with score-based neural networks that are trained on images of real galaxies. So the model has a good sense of what galaxies look like. And we can use this to help guide the fitting to reasonable solutions in very crowded and low signal-to-noise fields. And we've written the whole Scarlet 2 code in JAX so that it is GPU compatible, so it can be scaled up to wider survey analysis. So the other extension that we've done to this code is to be able to deal with variable and static sources. So we want to produce light curves across multiple surveys while using the fact that we know galaxies are static. So we're able to fold this into the forward model to model multi-epoch and multi-resolution data to create light curves across surveys while also coming up with the best galaxy models possible using the multiple surveys. So to summarize situations where this might be useful if you have a particular transient that is in both Roman and Rubin or Euclid. So we can use this code to produce a light curve across the surveys without needing a reference image without the transient. And the reason you can do this, especially when you have high resolution data, is that if you could resolve what the SED of the galaxy looks like around the transient, then you do not need to have a reference image without the transient. It's just all part of the forward model. And we've shown, even with AGN and nuclei, that we can do this fairly well. We can also, for example, if you really want to know the host galaxy properties, like the properties of the host galaxy of the transient, you can do sampling of all the posteriors, the galaxy nucleus, the, any of the parameters, you can come up with a full posterior if you really care about uncertainties for a particular object of interest. And finally, if you, for some reason, think there might be a transient somewhere, maybe there's a, a radio flare or something, you can do deep force photometry with some sort of prior on the position, if you don't know it very well. So these are just some examples of use cases where this might be good if you really want to analyze a transient in detail. But we're designing this in mind with big scale survey analysis. So for the gravitationally lensed supernovae, we want to be able to also model lenses in this framework. This is an example, if anyone's used lens astronomy, this is like the default tutorial, and this is what it would look like in a Euclid exposure and a Rubin exposure. And we want to be able to distinguish between the different components and come up with light curves. And this is a more typical Euclid and Rubin case where it's just a blob in Rubin. So we've developed a prior for what lensed galaxies look like to help with modeling the lenses. It turns out that we did not need to simulate 250,000 lenses and train a prior. Even though this works fine, you can also have a much simpler approach with starlets, which treat the fact that there is pixel-to-pixel correlation and can model the lenses fairly well in a non-parametric way. So just to show some examples of why we need to do this. So this is a Rubin image. This is an initialization and the final fit. And it might look like we have a good fit of this quadruply imaged supernova based on the residuals. But if you look at the morphology model of the lens, it's not so good. So we don't have quite enough information. If we fold in Euclid information, we're able to come up with a much more realistic morphology model. So now to look at the more realistic case, this is one where it's just a bit partially resolved blob in Rubin. And by folding in the space-based imaging, we can come up with a much better model for everything in the system, as well as extracting light curves such that we can measure time delays using the high cadence ground-based multi-epoch data for our time delay cosmography, so we can measure the Hubble constant. So at the moment, we've just implemented the capability to model these lenses in Scala 2. We have a student who's now looking at how well we can measure time delays by combining data across Euclid, Rubin, LS4, so we can have as high cadence as possible and extract good light curves from surveys where it is not resolved at all. And we have 4 lens supernovae in 1 PSF, and you need to extract the light curves. There are other examples of cases where we hope this will be useful. So Yuhan introduced this really exciting offset TDE that she found yesterday. And this is an example of a source where it can be useful to be able to have this forward modeling framework to get good uncertainties on transient host spatial offsets. So in this case, the difference imaging suggested a 1 arcsecond offset, but that's about the same scale as ZTF, which also has 1 arcsecond pixel scales. So when you look at this image and you're saying, it's 1 arcsecond offset, it can be kind of hard to convince TACs that that offset is real. So by doing the full forward modeling, we were able to get posteriors of the transient and host nucleus positions, and then she was able to get all of this awesome HST Chandra CLA follow. And finally, on the AGN case, AGN are always in your reference images, unfortunately. So if you care about getting host galaxy SEDs of AGN and AGN light curves that don't have some kind of absolute offset, this approach can be used to extract AGN light curves and host galaxy SEDs by leveraging the high resolution space-based imaging. And we've shown that when we do this method based on photometry alone and compare it to full spectroscopic modeling, we're able to extract host galaxy AGN SEDs well, even when the host galaxies are very compact and poorly resolved in ground-based imaging. Okay, so in summary, this software development effort is coming out of the Euclid-Rubin derived data products effort to provide a framework to, put all of our grounded and space-based survey together and analyze it in a way that really uses the strengths of all of the surveys. And we hope that this will be useful for transient science. If you have any particular use cases that we should add to the code, if you, are interested in implementing this for any of your science, please come and chat to me. We're kind of finalizing it now and documenting it. So it's a great time to give us some feedback if there's any way that we can help. So please come and chat. Thanks.
Thank you very much. Any questions? Go ahead.
Great talk. I was wondering if you have tested this code on Zwicky yet using the unresolved ZTF-like curve.
Yes. Yes, actually. So that was actually the first thing that I used it on because I was interested in things like looking for offset AGN in mergers, offset TDs. So yeah, in the methods paper, we kind of show that you can use it to extract ZTF light curves. You can get morphology models for complex low redshift host galaxies and things like that. The 1 /2 pixel scales are not a challenge for it. I would be interested to try it on like TESS or ULTRASAT data and see how it deals with the massive pixels, but it's fine.
I meant Supernova's wiki.
Oh, sorry. Yeah, no. So we will definitely go back and test it on previously studied lenses. At the moment, we're not at the stage of doing science with it. We're basically just made it capable of analyzing them, but we'll definitely do that as part of the next methods kind of testing.
Bob?
Could you say a word about the computational requirements for doing this elaborate stuff?
Right. So at the moment, it takes about the equivalent of rerunning the whole LSST pipeline to do joint analysis across Rubin and Euclid. So at the moment it's at the stage where there are large computational costs. It's like doing Rubin again, but it is computationally feasible. So at the moment we've designed ways to do joint analysis that are more computationally efficient. They're not full joint pixel processing to make the first stages of the derived data products faster. And the regime I imagine this being used at is for individual transients of interest, individual fields, and things like that. But if we hope in the future we'll be able to run this at scale for the surveys as part of the later derived data products.
Shall I?
Yeah, so I was very interested in this idea of doing non-parametric modeling of these structures. I was interested, so would this also apply, let's say if you had a strange structure of a source in the galactic plane? So there are what's this called? Crowdsource. The crowdsource thing, I think that primarily deals with point sources. If you had a really dense galactic plane field, could you create a model for, let's say, a dissolved outflow from some structure?
Yeah, so at the moment, I think the Starlet model would do a pretty good job with that. So this is, it would be, even in a more ideal situation, we would have priors trained on what these structures, images of what these structures look like, so that it really, was doing the best job possible. But at the moment, if you have a bunch of point sources and then some kind of correlated wispy structure in the background, the Starlets can model that.
Okay, then let's move on. Thank you very much. Then, yeah, thank you. And this is for you. Education. Let's see. Not this one. Good. Good. Your clock is there.
I see. Thank you. Hi, everyone. It's been a great pleasure to meet all of you. Many familiar faces, many new people. I also wanted to thank the organizers for making this very enjoyable meeting. Armin, Suzy, Ori, Takeshi, Youssef, and probably I'm missing some of them. So thank you very much from all of us. This is really excellent. One of the best meetings I haven't been to for many years. Thank you very much. I have a dual purpose in this presentation. One is to present to you ULTRASAT, which has already been mentioned in many talks. And the second one is to give you some ideas that I had about how it would be useful to study transients, and in particular supernovae. So ULTRASAT is a joint effort of many, many people. The PI is Eli Waxman, who is not here. And I want to highlight several other people that have been working on it a lot. Our program manager, Rudi Netzer, is dealing with all of these big industries, which is a big job. Eran Ofek is our science lead. Sagi Ben-Ami is the payload lead and has been working on the design of the instruments. Yossi Schwarzwald is the project scientist, and many of you, I think, are using his paper to learn more on this mission. And James Rhodes is the NASA project scientist. NASA is a partner in ULTRASAT providing the launch. And as part of this partnership, there are also 14 US PIs, and many of them are here in this room. And James is leading this partnership. So if you're interested in learning more about the opportunities offered by NASA, you are welcome to approach James. ULTRASAT has very high discovery potential because it has a very wide field of view, high throughput in the UV, and high cadence. So this combination, if you measure its potential to discover transients as a function of time, it's comparable to LSST. LSST has a deeper and wider area, but lower cadence and works in the optical. LSST is in the UV, ULTRASAT is in the UV. It's much more efficient than GALEX, who did some work very pioneering when it was still up. So there's a lot of potential, 200 square degree deep UV images in every 5 minutes. The PSF, as was mentioned here, is large, 8.5 arc seconds. So ULTRASAT will not provide nice images like we've just seen. For that, you will need to use other telescopes and missions. ULTRASAT will provide monitoring of a big chunk of the universe, providing cadences that we are usually not used to having, from minutes to continuously monitoring for months of the same area. And some of that has already been mentioned before, and I will also highlight some of the things that you can do. And it is geared up for TOO. It's very agile. You can reach 50% of the sky at any given moment in less than 15 minutes and stay there for at least 3 hours. So if you have ideas for good TOOs, ULTRASAT can, in principle, answer these. This is what the mission will do. At the beginning, there will be an all-sky survey where we try to cover the entire sky to create a deep all-sky UV map that will be significantly deeper than GALEX, and will cover also areas where GALEX did not observe. And it will also serve as references for future visits of basically everywhere in the sky. This map will be made public through our collaboration with the Rubin collaboration. There will be what we call long stairs. ULTRASAT has optimized fields, one in the north, one in the south. We'll spend 6 months out of each year, either in the north or in the south. And in these directions, which are close to the ecliptic poles, 21 hours out of every day, we will just take continuous cadence of 200 square degrees every 5 minutes. And then in addition, around these areas, there will be significantly larger areas, 2,000 or 8,000 square degrees covered in cadences between 1 and 4 days that can be changed during the mission lifetime. So this will provide lower cadence coverage of a big chunk of extragalactic sky. Actually, this is probably most of the useful extragalactic sky you can observe with ULTRASAT, because once you move into areas with extinction, the efficiency of the observations falls significantly. The data is downloaded continuously in real time, analyzed on the ground. There will be alerts within 15 minutes of observations, as I said, and TOs are acceptable. There are some parts of the sky where ULTRASAT does not have enough solar illumination on the panels, and there is a limitation on how many times we can recharge the batteries. So there are specific small areas where we cannot do unlimited number of TOs, but most of the skies we can do. And then there's continuous transmission to the ground, even from those remote areas everywhere. Status, okay. So as you can see, things are being produced. This is the main mirror of the satellite. The structure. Let me see if I can stop this. Yes, good. So most of the technology risks has been retired. So the sensors, which are new technology, are very efficient, low noise as expected, and they are now being packed into a camera. Most of the big stuff, as you can see, has already been bought and produced. The launch is expected to be end of 27 or beginning of 28, and NASA team is working on the launch provider. There are still some risks that we are keeping track of, in particular contamination, which is problematic for UV mission, and of course keeping that timeline, which is synchronized with other things that I will talk about in a second, and we don't want to miss. The mission cost is approximately $100 million without the launch that NASA provides at its own cost. Okay, sorry about that. Okay, now going on from mission to science. So what can ULTRASAT do for you? Let's start with the gravitational wave counterparts. So according to current schedules, ULTRASAT and LVK-05 will occur more or less during the same time, and beginning end of 27. And during this period, we are sort of expecting to have something like a few, maybe 10 neutron star mergers each year, well localized, and these will be very efficiently covered by ULTRASAT, perhaps even in a single pointing, and if not in a few pointings, and ULTRASAT can do this very efficiently. We cannot observe close to the sun, but actually most people can observe close to the sun unless you have a radio telescope. But the areas that are observable, ULTRASAT can cover quickly and efficiently. The sensitivity is such that events similar to the known kilonova from 2017 can be seen well outside the range of the current LIGO sensitivity. And in addition to detecting these transients, we will provide continuous UV light curves that will be very useful to determine things like bolometric properties. This thing here below, let's see if I can see this. This I prepared here in Baltimore in 2016, before the 1 kilonova was identified. And the reason I made this plot was to illustrate my thinking at the time that kilonovae should be UV bright. And I still think this is true. Early on, there's the free neutron decay. Everything is very radioactive, highly ionized. So I think even with a lot of heavy elements, at the beginning, I can see how these things are not blue. And therefore, I think ULTRASAT will be a very good way to find them. They could turn red quickly, but ULTRASAT is even quicker. And the UV is a good way to look for them because compared to other things, it has less limitations. X-ray, gamma rays are excellent, but if the thing is jetted, you only get very few of the objects. Radio is very good, but it takes a long time to come up. And the infrared is faint, and as we learned, at least in some cases, it takes a long time to come up too. This is the topic of working group 1. The lead of that is Eran Ofek. So if you're interested in that, he's the person to contact. Supernova are also a main target of ULTRASAT, and this plot has been shown several times. So ULTRASAT will be efficient in finding supernovae, finding one young supernova at age less than a day every day, more or less. And let's say every month or every couple of weeks, finding supernovae that are about 1 hour from explosion. Originally, we were thinking to map the shock breakout. So a shock breakout from a bare red supergiant should be something like 30 minutes, and the cadence of ULTRASAT should resolve that. Jared, who is somewhere here, explained why in many cases this signal should be smeared to several hours. especially if the system is asymmetrical. And this is great because how else can we learn about asymmetrical stars except from measuring the signal? So I think it is excellent. And of course, if there's circumstellar material, this could be further smeared, as we already heard. Our ground-based work so far suggests that about 50% of the events do not have a lot of CSM. So perhaps we will still get to see the bare stars. And I think until ULTRASAT is launched, we really will not know the answer to that. And I'm personally working on this for like a decade, so I would really like to know the answer. So there will be a lot of supernova science, and we will learn more about shock breakout and then shock cooling for a large sample of supernovae of many different types. I lead this working group on this topic, so if you are interested, you can talk to me. Let me stop here for a second. I don't have slides for all the working groups. We have 13 of them. However, some of the working group heads are actually here. So Brad is here. Where is he? So he leads the working group on GRBs and fast transients. So you can talk to him about that. And we have another one. Yair and Suvi are working on TDEs. So if you are interested in that, you can talk to them. And I think these are all the working group leads that are currently in this room, but on our webpage, you can see all the working groups and who you want to talk to. So if we are thinking about supernovae, just to illustrate the sort of data you can expect. So this is a simulation, but it is, I think, very realistic. So this is what you would see. The UV rises before the visible light, and you would have very highly sampled UV light curve from ULTRASAT that provides a trigger for you, and then there will be follow-up in other bands from the ground or from other missions. And as Erez already showed, and also Wim talked about this, this could be used to map the CSM around supernovae where there is CSM very, very well. Okay, let me just give you a few more brief ideas. A cadence of 5 minutes is really great to look for short flares. Now, in principle, you would have said, okay, but there are no short flares from transients, but well, really there are. So Anna Ho and I think Dan showed this. This is 1 year, or not, sorry, 100 days after a fast transient. We were trying to study the host galaxy, and we discovered these minus timescale flares. Very unexpected, probably coming from the compact object left after the explosion. And ULTRASAT will be able to look for such flares for everything, for all supernovae, for all transients. I think it would be very interesting, and there's no comparable data set to that. This is how it looks at highest temporal resolution. So you can see that the minute timescale is really, would be very useful. Another thing that happened last year, there were many talks here where people were talking about binaries and how supernovae and other transients come from binary system, but now we have at least one example where we actually see the binary signal as a periodic signal in the light curve and also in the spectra where the emission actually moves periodically. And again, this is, the period here is 12.4 days. So that you can do with ground-based photometry, and it was done indeed by Ping Chen using Atlas and ZTF data. But these periods can be shorter, and if they are shorter than a day, of course, it's totally impossible to do from the ground, and you can do it with ULTRASAT. So I think it would be very interesting to look for additional periodic signals in light curves of transients. The last thing I wanted to say is related to this diagram that has already also been shown, which is the mapping of the time scale of transients. So we've been pushing to shorter and shorter transients, faster and faster transients, and now we are sort of hitting this wall of rise times of 1 or 2 days. Going below that is difficult because the surveys have typical cadences of 1 day. But the time it takes the Earth to revolve around its axis is not a basic fundamental physical property. And there's no reason to think that there are no transients that are faster than a day, maybe on timescales of hours or even less. And ULTRASAT can easily find those things that rise quickly, that decline quickly. And I think this is a very interesting frontier, both extragalactic and also from stars, of course. And that's it. I'll stop here and we'll start. Thank you.
Questions? No?
for kilonovae like black hole neutron stars also would be a candidate?
I think so, yes, because, well, the predictions, and I think Brian is here, or at least was here. So the prediction for black hole neutron stars, they will be very red very quickly. But again, as I said, in my opinion, I don't see how you take neutron star and turn it into red absorbing material immediately within minutes. The neutrons should decay. There will be very short-lived radioactive elements. Everything will be highly ionized at the beginning. There will be electron scattering. It's going to be, I think it's even neutron star black hole major should initially be UV bright.
Last question.
What are the plans for QOs in terms of who can trigger or how the triggering works?
Yes, so that has not been decided. ULTRASAT will accept TOOs. We definitely will follow up gravitational waves, but in principle, there could be other TOOs. We have to be mindful of, not interrupting the continuous monitoring too much. And also ULTRASAT has 200 square degrees field. So if you want to do a TOO on, let's say, a single object, it really has to be very well justified. If you already know where the supernova is, SWIFT is much better tool to follow up than ULTRASAT. ULTRASAT only gives you one band, and you are wasting this in huge field, while SWIFT can give you multiple bands and X-rays and so on. So there will be a process through the director and through the science board. I'm not sure exactly what it's going to be yet. We will surely accept TOOs, and exactly what they will be and what will be the policy is yet to be determined.
Good, then. Thank you, Avishai, and all the speakers in the morning.
All right. Thank you, Avishai, for buttering us up. ULTRASAT is now my most favorite future mission. But don't despise. Shoot myself in the foot on that one. But don't despair, everyone. We have the afternoon session is on future missions, so you all still have a chance to butter me up. And it's going to be lunch. We're running a little late, so let's come back at 2 o'clock. All right.